Good evening, everyone. Welcome to the BCS. I'm Jos Crease. I'm the BCS President for 2015-16. It's my great pleasure to welcome you all to this annual Karen Spärck Jones lecture. This is the 5th annual lecture celebrating women in computing research, sponsored by the BCS and IBM. A little bit about Karen Spärck Jones. She was a Fellow of the British Academy and Vice President for 2000 to 2002, and she was an early pioneer of advanced computing and information science, right back to the early days in the 1950s. This annual lecture has been set up in her memory, and we're very grateful to IBM, who've been the sponsors for several years and are continuing to do so. We're delighted this year to welcome Dr. Cornelia Schmidt, who will give the address. It's now my great pleasure to hand over to Paul Martinenko, IBM Vice President and Technical Executive, who will introduce tonight's speaker. Thank you, Paul.
Welcome to everybody, and thank you for coming. We're greatly honoured to sponsor this lecture with the BCS. I'm also Vice President of Professionalism for the BCS as well, so I'm a trustee of the Institute. So it really is great that we continue to do this and so many of you come tonight. Today's topic is a very important one, and our guest is a very important one as well. So, to Cordelia, thank you very much. As we move towards a smarter planet, as computing starts to invade everything in life, then being able to see is probably one of the biggest challenges that we face. Being able to perceive what is out there, to make decisions based on that perception, which are then accurate, reliable, and everything else, is actually a very important part of the next phase, if you like, of computing. Dr. Cordelia Schmidt is a leader in that field, okay? And we are delighted to welcome her tonight. She works at INRIA in France as Research Director and Head of LIA, the Learning and Recognition Vision Project Team. She holds a MS degree, Master of Science degree in Computer Science from the University of Karlsruhe, and a doctorate in Computer Science from the Institute of National Polytechnique de Grenoble. Her doctoral thesis on local grey value invariance for image matching and retrieval received the Best Thesis Award from INPG in 1996. Dr. Schmidt was a postdoctoral research assistant in the Robotics Research Group at Oxford University between 1996 and 1997. Since 1997, she's held a permanent research position at INRIA. She's authored over 100 technical papers and has been an associate editor of one of the IEE magazines and IUCV, editor-in-chief for UCV, program chair. So publishers passionately for the subject that she's here to talk about tonight. In 2006 and 2014, she was awarded the Longuet-Higgins Prize for Fundamental Contribution to Computer Vision, and that have withstood the test of time. She's a fellow of the IEEE. In 2013, she was awarded an ERC Advanced Grant. In all of that, she also supervises 20 PhD students. So not only a leader in the field, but also a leader in helping others come into that field. So artificial intelligence, perception, Dr. Cordelia Schmidt.
Okay, thank you very much for the introduction. So today I'll talk about automatic understanding of the visual world, and I come back to what that means in a moment. I had prepared a few personal details. I'll just go over them quickly. Then an introduction what machine visual perception actually is. Then I'll go over the history of perception, the current state of the art, and what's important for the future. Okay, so as Paul already mentioned, I'm an INRIA research director. INRIA is a French research organization which funds researchers, similarly to, for example, what's the Max Planck Institute in Germany. And you can see here the locations, several locations all over INRIA. And I'm actually working in the south of France, in the French Alps. You can see here an image of my environment, and on the bottom you can see our location. So we have a very nice building and we have very good research support. Okay, I'm a leader of the LIA research team, which means Learning and Recognition and Vision. The team was funded, so in INRIA we have specific teams which have a specific time length and a specific project to accomplish, so it's for 12 years. And so it was funded in 2003, and at that time it was novel to add actually machine learning techniques to vision. So what I'm really working on is at the intersection of applied mathematics and computer science. So it's not only computer science, but nowadays we really need contribution of applied mathematics or machine learning to handle the problems, the open problems. Paul has already gone over my CV. And so what is machine visual perception? So if you look at on Wikipedia what machine perception means, is that a computer understands its environment. So it's not only vision, it's also audio, sound, speech, and also these days touch, and even further, it goes even further, smell. Okay, so I'll concentrate in this talk on visual perception. So what we want is we want the computer to understand the content of images. And so if you want to know why this is difficult, so what you see here on the left, an image, what it is, it's a matrix of pixel values. So what the computer actually gets in input is this matrix where, for example, if it's a gray value image, the values range between 0 and 255. So that's all the computer sees, and from there on, it has to determine what's actually in the image. So this just to give you an idea of how difficult it actually is. Because if you think, as a human, you look at this image and you think it's trivial to solve this task, but if you think of what the computer sees, if I give you this image, you're all not able to know what's in there, right? And so the task here is to help the computer learn what's in the image. And here, for example, one of the tasks is object localization, to determine where in the image the cars are, where in the image the cows are. And then if you want to go further, you can go to videos where you have not only one image, but a sequence of images. And then you want to see, for example, what are the actions and activities which are present in this video material. Okay, and then today, there are already quite a few applications which have come to the market and which start to really work. So if you look, you'll see that in a moment. If you look what was there 20 years ago, basically things did not work, but today there really start to be applications which do work and which are used and which you're probably all familiar with. So one is, for example, face detection. You probably all have your own camera, and in your camera you have actually face detector. This helps to set the autofocus. And then also it's the first step for face recognition. So for example, on Facebook, you have face recognition tools which recognize the users. You can see here that if the faces are frontal and not too much occluded, they can be actually detected very well. Another application is in car safety. So many of the car manufacturers work on pedestrian detection. You can see here, for example, this is the application for Volvo, who actually has a brake if they detect pedestrians. So again, you can see pedestrian detection starts to work very reliable. And this is another example for video surveillance. And what you can see here, it's still difficult because you have very many humans here, and the algorithm actually manages to detect the ones which are in the front, but for the background ones, it's still difficult. Another thing which you probably also have heard about or might have heard about is Google goggles. So there are many different companies, small startup companies which have developed similar applications. So what's the goal in here? You take your smartphone, you take a picture of, say, a book, cinema, or any kind of product. What you get is you get information about what it is, where you can buy it, and so forth. So for example, one application would be you go around the museum and you get information about the paintings. And these things start to work well nowadays, okay? And so, just coming back to this initial description of why this is difficult. So it's difficult because an object can be seen from different viewpoints. So if you think of a human, you can see it from the front, from the back, and it's completely different. If you look at this pixel matrix, it's completely different. If it was exactly the same, it would be obviously very simple. The illumination can change significantly, and this makes it difficult to see why it's actually similar. So if you look at these two images, if you just compare them, a simple comparison of the pixels, they're completely different. So what you have to do is you have to localize the parts of the image which are similar to put them into correspondence and to say that this is the same object. And here, if you look at the viewpoint, again, if you see something from a different viewpoint, it's obviously not completely trivial to say that it's the same thing. So what you have to do is you have to store not only one view, but several views. And then here, lightning, you can see basically at some point, even for a human, it's impossible to detect the building. And so there actually, sometimes the computer can be do better because there you can bring in some illumination normalization. And another difficulty is occlusion. You can have objects which are only partially visible, and again, then things get much more involved, right? And then the second type of problem, so we've seen this is like if you have just one object, so one person, for example, and when it gets much harder even further, if you have an object class, right? So for humans, it's trivial to say that here, this is a chair, but if you think of what the computer has to do, it has to learn the whole variability of all these different chairs. And so that's actually where today's approaches for the machine learning aspect comes in, because you really have to learn the variability of this feature space, right? Because if you want to store all possible chairs, it's just not possible, okay? Because that's the second difficulty in class variations. And then if you go to actions, the problem gets even more complicated because there the definition of what an action class is even unclear today. Okay, and so now a small overview of the history of visual perception. So I'll start the overview in 87. So there was some work on pattern recognition before that date, but this was ICCV 87 was the first computer vision conference, which was actually held in London. And so what the approaches at that time were, at that time the machines were not very powerful, so what people had to do, they had to first extract edges because they could not handle all the pixels. So they had an approach which extracted first edges with very simple filters. So edges are gradients of the gray value, so what you have is you have black and white, and you can calculate the difference between this black and white, which is simple, for example, Sobel filters, -101. And this gives you very quickly this edge image, right? And so then the next step was to match a 3D model to the 2D points, project the 3D model to the image, and verify if this was the correct model by measuring the alignment between the projected edges and the edges in the image. And so here you can see this object here with this approach was detected correctly. But of course, if you think of real-world applications, this is very far because it's much too simple models. The task is simple, can handle only a few images, and it was handcrafted. So maybe if you think of what are the lessons learned from this, basically the lessons which are learned is that some verification step after the initial matching is something which is still used today. Okay, and then another type of approach, which was amongst others developed by the people from Oxford and the Similarity, is based on projective invariance. So this was actually theoretical work where people derived invariance based on, say, 5 lines, 2 conics, and so forth. It was a very nice mathematical point of view, but the problem here was twofold. So here what you do is you first detect conics and lines, and then measure for all combinations the invariance and use that to detect objects. And the problems were twofold. The first problem was detecting all these features. It was very hard because you have to be very precise to detect the lines and conics. And the second problem was that these projective invariants only exist for 2D planar objects. Okay, but what has remained? So again, what has remained is the idea of invariance in computer vision. I'll just explain what it exactly means, because invariants appear in computer science in all different forms. And here what it means is that if an image undergoes a transformation, the value of the function remains the same. So for example here, if you have a similarity transformation between 2 images, so if you have a translation, a rotation, and a scale change, the invariant here would be the angle, right? If you have this rotation, scale change, the angle will remain the same between the 2 images. And this is something which is, even today, if you look at, for example, the deep networks, these invariance properties are very important because you have to deal with some type of invariance, as I mentioned in the beginning, because you cannot just model everything, every object from all different viewpoints. You have to have some invariance properties built in. And the second example from invariance, which is very powerful, is based on photometric descriptors. So what you do here is you have the estimated region, which is identical in the 2 images, which is covariant between the 2 images, and then you can extract a normalized gray value patch. This again will be invariant to the scale change. Okay, just so for a personal note, so I did my master's thesis in '92, And at the time I worked in robotics, so it was mobile robotics, and what you needed is you needed to calibrate your stereo head. And so here, what the problem was at the time is actually to precisely localize these interest points. So that's actually what got me motivated, the problem of computer vision, because I mean, we spent quite some time, so the mathematical formulations, they're pretty, I mean, they're easy to derive, and once you have derived that, the remaining problem is how you can localize these points precisely. And at the time, remember what I said, you only had at your disposition edges and simple interest point operators, and they failed all the time. So basically, I thought, this is not possible. If you look at this image, it's completely simple to localize these points here, and the computer is not able to do it. Obviously, if you think of it not today, with the methods we have today, it is possible. But if you think even further, if you look at robot applications today, if you have any kind of objects and you want to detect them and grasp them very precisely, it's still an open problem, right? And this was just like a small thing why actually I got interested in. I thought this has to be solved. And I think from where we were there, so that's more than 20 years back, we have made a lot of progress in the field. Okay, and then in parallel, a few years later, methods appeared actually which modeled the appearance. So far everything was based only on the geometric relations between points and edges. So here people started to use, that's what's still used today, the appearance of the images. So they used the gray values, and here one of the first techniques which started to work for face recognition was the eigenfaces from turbo-10. What they did, they had a very small set of people, so 16 people, and for each of them many different viewpoints. And they modeled this set of images by doing principal component analysis. So what you get is you have a collection of images, you extract the principal components. What that gives you is the average image in the different directions of your point cloud, right? And so what you have then, you have a compact representation. So they took 7 of these eigenfaces, and these are the eigenvectors, so the corresponding eigenfaces, and they use this representation, these bases, to represent a new wave face. So what they do is they project the face in this eigenspace, and then they have this vector W, and they can use that then to find the most similar face in the data set. This is a very simple technique, right? You just project the image through the space, and then you search for the nearest neighbor. But it was one of the first approaches which really managed to recognize faces for a very small set. Okay, and then this technique was also applied to object identification. So here what you can see in 2D, so you project the car to 2 dimensions, and you model the appearance variation by a manifold, right? And this shows you how different actually how the car varies over the space. Okay, and then here, you can see here, this was actually maybe one of the first systems which managed to recognize the object as well as the pose, right? So here you see the object which is identified, and underneath you can see the pose which was determined automatically. And so this data set was still very small, so 20 objects, and the objects were taken from on a bad background. Okay, and then a few years later, so what the idea was to get rid of this global information is to compute these local appearance descriptors locally, right? So you've seen here all these face descriptors were computed on the whole face, and the problem is if you have clutter in your scene, you cannot take care of this clutter, right? So if you have, for example, if you have occlusions and background clutter, if you have a global model and you extract descriptor for the global image, you cannot get rid of this occlusion, right? And so the idea here was to model the appearance of an image by a set of individual local descriptors. And so each of these local descriptor was described as some sort of invariance. So here, for example, it was differential invariance. There was a lot of work, and there's still work ongoing, on which descriptors are best to describe the content of the image. And then here, what the idea is, it's very simple. What you have, for each, you store the set of images as a set of descriptors. For each image you have, so here for example, 2 descriptors. For each image, I1, I2, IN. And then you measure how similar the descriptors of your query image are to those in the data set, right? So you have a large data set, and that's actually what's behind all these image retrieval search engines which are available today on the market. So you have a set of images. For each image you store a set of local descriptors, and then this is a very simple scheme for voting, and then you have nowadays many different schemes for indexing very quickly these local descriptors, right? And so the idea is, here it's simple, you measure which descriptors are similar, how many of them vote for the different images, then obviously you can have many variants. I'll come back to one in a moment. Many variants on how you vote, how you measure the similarity, how you describe the geometric relations. And if you look at the results here, what you have here, you have more than 1,000 images and objects, and you're able to index and find objects in the presence of background clutter and occlusion, as well as camera rotation and scale changes. Okay, and then a few years later, the descriptors were made more robust. That's the very popular SIF descriptor. And so here, the idea of robustifying these local descriptors is based on some invariance properties. So basically, you want to be locally invariant to changes by introducing these small grid cells. So this is one of the most popular descriptors in the literature. And so this guy, David Lowe, he also put together a whole system. And one of the components, just go over this very quickly, which is very important and which is still very important, is actually what I said, is this geometric verification. Okay, so what you have a set of these descriptors extracted. You match them by some similarity function. So for example, the descriptors which are similar, the SIF descriptors which are similar. You get a lot of mismatches because these local patches are not all discriminative. And what you do then on top of it, you estimate robustly the geometric relation. So basically you have a set of matches, you take a subset of points which give you an initial solution. For each of these initial solutions, you vote how many of the matches correspond to this initial solution. You can either do this with a half transform or ransack. The idea is really to robustly measure what is the relation between the two images, and this allows you to measure the inliers and the outliers of the initial matches, right? So basically the idea here is once you have a set of matches which are given, you can use these techniques to verify the matches, and in the end you get a number of inliers which you are sure that they match between the two images, and they really measure the correspondence between the two images. So if you have a whole list of images which are returned by your algorithm, you can use that to verify. That's what I said in the beginning. This is kind of this approach. You first get a solution, and then you verify that it's the correct solution. That's something which is still used in any of the image search engines. This is the basic approach. Obviously, then people refined it, but the idea is still there. And very important. So what he could do then, David Lowe, he could use that to recognize these images, these objects in a test image. This is a test image. This is this library of objects. He had 20 objects, and he could recognize then the objects under different viewpoints in a cluttered scene. Okay, and so these all the techniques I've shown so far, they're based purely on image features. And so then in the early 2000s, people started to add actually machine learning techniques to the image descriptors in order to measure the variability across categories, right? So one of the first was Viola Joins, the Viola Joins detector. It's a detector which is still an OpenCV, which is still used today. And the idea here is, and it runs in real time, so the idea here is to first extract Harlet-like filters, which are very simple, can be calculated very fast with integral images, which is a trick for fast calculation. And then what's important here is they have added on top of this a boosting algorithm for feature selection and classifier training, right? So what you have here, you have a set of positive and negative images. What you want to learn is you want to learn the separating boundary between the positive and negative images. And what you can see here very nicely, you can see here the two first filters which were selected by the approach. You can see that those actually characterize intuitively what you would think is important for a face, right? To recognize a face, it's important that there's the eye bar here, with the front nose here. And if you look at another, so this is important actually, so when you train a face detector, you don't want to train only frontal detector, you also want to train a profile detector because the appearance, what I said before frontal and the profile is completely different. So here just images used for profile training, and then here a few selected features for the profiles, just to illustrate the approach. And so here you can see the results for frontal and profile faces. And what's important is that the code is available in OpenCV, so students who want to use this code, they can just download it and run it immediately, and it's still something people do use today. And then in parallel, another approach which was developed for pedestrian detection, so again a similar idea, different descriptors, different learning methods. So what's done here is that the appearance is described instead of using these hard filters with a histogram of oriented gradients. You put on the image a grid, and for each of the cells in the grid, you calculate a histogram of orientations. So this would be the histogram of orientations. And what it does, it measures locally what is actually the dominant orientation of the edge in this cell. So if you look here, for example, along the person, you would have dominant orientation in line with the person, right? And then on top of this, this is the descriptor which you extract for the training image. On top of that, you use a support vector machine classifier. So support vector machines are one of the standard techniques today, still today in machine learning. So what they do is they learn the separating hyperplane between the positive and negative samples. And what you can do with the classifier you learn is linear. You can actually show the positives and negatives rates which you have learned. Okay? So what you do is if you have a test image, you multiply the test image with this classifier vector. And what you can see here, it has nicely learned the features again of the human. It really manages to capture what's common across the collection of pedestrians and not in negative images, right? So this is kind of the intuitive idea why you want to use learning, right? Because you want to get rid of all the features which are not significant and keep what's relevant to the category. That's exactly shown here, right? And so, for example, if you look here, all the bars in the middle will be like the jacket and things like that. They're negative because they don't count as they're not important for a human. Okay, and here just section for individual frames of the video. So this is the original video from 2005. So obviously by adding some linking between the frames, you could further improve the results, but you can really see that if the pedestrians are upright and clearly visible, the results are very good. And obviously if the pedestrians are now crouching on the floor, things like that, the problem gets much harder, right? So that's why it's not solved. Okay, and just to come back to this idea of machine learning-based classification. So just to explain what's going on here, what you have is you have a set of features which describe the positive and the negative images, right? So you have a patch for which you extract the features. This feature vector, okay, here is in 2D, will be represented in ND. And what you then want to learn is you want to learn the decision boundary which manages to separate the positive images from the negative images, right? And so what's important here is obviously the quality of the image features. What you want them to be as discriminative as possible. You not have them all lie exactly on the same spot. You want to have them as distributed as possible. Then, so that's why people have spent quite a lot of time on how to design these image features. The second thing, obviously, which is important, is the machine learning approach. So how, once you have the examples and the features, how do you measure the boundary? This is work in machine learning, where you can really predict what's the training error, how do you overfit So what you don't want to fit too tightly, because then otherwise the testing images are not classified correctly. There's also the difference between obviously speed and precision, right? If you have a nonlinear classifier, it's much slower to evaluate. And the last open point is actually the examples. And it's maybe today often the most important point, right? How do you subsample the points which represent your class to make your approach learn as well as possible, right? So one of the things which is very important is how do you sample the negatives. So you have to have negatives which are not too different from the positives, because otherwise the information is far down here and you don't learn anything. So you want to sample the negatives which are close to this decision boundary. And then the other point is the positives. So there's actually quite some work going on this, because what people often do, they tend to overfit to one data set, right? You have some subset of the data, you have a similar training and test set, you overfit to that. If you want to deal with real world problems, you really want to have a good distribution of the real world, which is in some cases like pedestrians or faces relatively easy, because the things in the real world, they're all very similar. But if you think of my chair example from the beginning, if you really want to sample all the chairs, it's not clear how you proceed precisely. In the end, if you want to have at least excellent performance, you really would like to not fail at all, right? I mean, that's kind of the final goal. Okay, and then once you have this decision boundary, if you have a new point, you can then predict if it's a zebra or not a zebra. Okay, and so this was history, and so now what's the current state of the art? So things which really work now is image retrieval. So what you want to do here, as I mentioned before, you have an image, say for here for Venice, what you want to find in your collection is similar images in this collection. So this would be the example, you take a photo of a book and you want to find the corresponding book in your data collection, right? And so the work which has been going on and which is more or less, I would say now we're in a state of the art which attains very good performance, is on these local invariant image descriptors. So these local invariant image descriptors would be at the same time descriptive and invariant, right? So the descriptors which we have today at hand are invariant, which we saw before, to scale and local affine changes. So if you have a scale change or rotation or local affine transformation, you can actually model these local descriptors to make them invariant to these affine or scale changes, okay? This we have, and once we have this collection of local descriptors, what you need is a fast approximate search of these descriptors, right? So if you think of what people want to do today, they want to scale up to millions or billions or whatever images. And so obviously, if you just store all these local descriptors, say you have 500 per image, if you store them all in a table and you search for them sequentially, it's much, much too slow, right? So what you have to do is you have to do fast approximate search algorithms. And so there's a lot of work which went into indexing schemes. We actually have a set of hierarchical indexes which you go through. Then you have a set of refinement methods where you project the descriptors to much lower dimensions, so you project each descriptors to a binary code. And then here, similar, you approximate this by hierarchical trees. And then if you think of this, if you want to scale even up, even higher, what people then do, they cannot afford to represent each feature descriptor individually anymore. They have to compact the information which is contained in each image. So basically what they do, then they aggregate all the local descriptors in a robust aggregation scheme manner, and then search the database based on these individual aggregated vectors. And obviously all this comes as a trade-off between speed and accuracy, right? And so one thing which is very important here, which I said before, is once you have a list, a ranked shortlist, which comes back from your approach, what you can then do, you can do geometric verification, right? So once you have, say, a set of 1,000 images which is returned by the computer, then you can afford to precisely verify, is this the corresponding image or not? Okay, and so this is what you see here. It's the same image of the same place, book, or object, right? And so maybe just to say what doesn't work, so this works very well For textured objects, it works less well if the object has very little texture, because then all the invariant descriptors are not that distinctive anymore, and it cannot be found so easily. Okay, and then the next problem is image classification. So image classification, the problem what you want to do is you have an image and you want to assign a set of labels to the image. So you don't want to localize what's in there, you just want to say the image contains a car and a cow. I guess the problem might seem a little artificial, and maybe possible applications would be if you want to index your images which you have in Flickr, right? If you have in Flickr, you want to predict the tags and you just want to add the tags automatically. Or you want to group then your images based on these tags. And so what has recently shown very good progress, and which you probably also maybe have followed in the press, are the deep convolutional neural networks. Yes, that's what you mentioned earlier. And they have shown to give very good results recently on this kind of problems. And if you look at what has happened, neural networks and even convolutional neural networks existed since the early 90s. And at that time, people managed to get them to work for simple problems such as digit recognition, or it's mainly digit recognition, handwriting recognition. So one of the open questions today is actually what makes the progress. I'll go into details about this approach in a minute, but here just to say what makes the progress between the approaches which were developed in the 90s and which exist today. And so I guess the common answer today are several things. First, it's the data. There's much more data. These models are very, very high dimensional, so there's much more data to train them. Second, the computers. They need a lot of resources, particularly GPUs, to train them. And then as well, there's more understanding about the approaches. So people now know better how to formulate the statistic gradient updates and how to select the correct nonlinear functions within the network. So all these factors make that this works now today, and there's a lot of work now going on in this area. And then other approaches which have given good results in the past are these aggregated descriptors, which I mentioned briefly before. So in particular, the bag of features and the Fisher vector, which is assembly of local descriptors into high-dimensional vectors. And the current trend is actually to combine these two types of approaches. So this is the most recent methods which are just coming out. And just to give you a small overview of these deep convolutional networks. So what's the idea? The idea is, I guess it was inspired by the brain. Basically, people looked at how the human brain worked and then kind of tried to model this. And so what they say, basically, in the human brain, you have a set of filters which are hierarchically stacked on top of each other. Okay. So anyway, that's the inspiration, but what's going on concretely? What you do is you have a set of convolutional nets. So you have a set of filters. I guess the first layer would be very similar to all the traditional image features, where you just take a set of convolutions. When you look at with your image, it's similar to the Garber or gradient filters. Okay, and then I'll just show that in a minute. And then the next steps would be to pull together regions in this correlated map, right? So what you do is you stack one layer on top of the other and summarize the content into hierarchical, more and more complex filters. And so here, this is just one layer. So what people do, you have this correlation, and you have the subsampling, where you do pooling. So you do max pooling, so you group together information. The idea behind that is that basically, if you have small shifts in the image, if you do the pooling, you get invariant to these shifts, right? It's exactly the same thing what we have seen with the binning before. If you have these bins, you can be invariant to the small shifts. Exactly the same idea. And then apparently what's very important here is this nonlinearities. So once you have these maps, you apply a nonlinearity that allows you to add in your model a nonlinear function, which makes your model much more powerful. So here what people nowadays use is a regularized linear normalization. Okay, so once this was like one layer, right? So this would be one layer here. What people then do, or what's then done in these deep convolutional networks, you store these different components one on top of each other. Okay, so you have here 1, 2, 3, 4, 5 of these convolutional layers, In the end, you have two fully connected layers. Okay, so what you can see here, A, it's pretty hard to interpret what's really going on, and B, it's extremely complex. So if you look at the parameters, you have 60 million parameters here. Okay, and it's very hard to optimize. It's very hard. You need a lot of data. You have to have it run for a long time to really get this network to be optimized, right? So you need a large data training set, and you need implementation on GPUs. Okay, and the data set on which their approach showed its excellent results was the ImageNet 12 challenge. So here you have 1,000 categories and 1.2 million images. Okay, so if you look at the categories, you can see here from A to H, the ones which are easy and the ones which are harder. So the easy ones are, for example, here, whatever, Jaser, Caricot, and harder ones, what you can see here, all the objects are very similar, so it's kind of easy for the computer to recognize them. What's harder if you have like tiny, thin objects like paintbrush, right? This is just, it still shows that even if the approach is powerful and improves over the state of the art, there's still open problems which people don't know how to handle. And also if you look at this collection of images, the content, in many cases, they're just centered on the object, which makes the problem also easier. Okay, and then a problem which we've seen before, so for face detection pedestrians, but in general for object localization, what you want to do on top of just classifying the image, now you want to classify a local region. So basically here, what people do, they have been doing for a long time, sliding window approach. They slide a rectangle over the whole image, and for each of these rectangles they extract the features and classify them as containing the object or not. And so here, the two things which are novel is that A, you extract, and then you have a mechanism for extracting relevant regions, a few relevant regions, like the interest points which we saw before, in advance, and then through state-of-the-art methods apply then these convolutional neural networks on these extracted regions. And so here, you combine actually the power of the computer vision algorithm to extract the regions with these powerful CNN features precisely localize the object categories. And then other approaches have been using region-based high-dimensional features and histogram, flexible histogram gradient approaches. And so I guess image classification results are today relatively good, and for object localization, people still operate on data sets with a limited number of objects. So I think state-of-the-art approaches work on data sets with about 100 objects. So it's still one of the harder problems. And it works well, as we've seen before, for specific objects like faces, where people then also go ahead and collect millions of images, like people from Facebook, they just collect millions of face images and train on that. And here, we'll see that in a minute, obviously you cannot train for every object category in the world, millions of images. So I'll get back to that in a minute. Because then you need to go to other techniques where you don't need fully supervised annotations. Okay, and the last thing is this video, so action recognition. So there's a set of approaches. The approaches which give best results today are the dense trajectory features. There's also CNN features which are used for videos. And if you look at what the task here is, so here you would see a very short action, so for example, answering phone. What you want, if you have a video stream, you want to localize this action in the video stream, right? And another application would be classification of video clips. So you have, for example, on YouTube, users who put up their birthday parties. And then what you want to do is go to YouTube and find, for example, examples of birthday parties. And this is actually an example of the TrackVid multimedia event detection task. So that's something which is where IBM also participates. It's sponsored by the stand. So there, they really went and saw what the users are interested in. People are actually interested in classifying these videos. Okay, and then here, a short explanation about these trajectory features. So what are these trajectory features? What's the idea here? So if you go to video, you haven't seen any approach to video, but then the problem gets more complex because now you have to capture at the same time the image information and the temporal information, right? And obviously what you can do is you can process every frame individually, include the things together, but that's suboptimal. What you really want to do is integrate at the same time the information, the spatial and temporal information, right? And so here, the approach is you extract small temporal trajectories based on the optical flow. So optical flow measures between subsequent images the displacement of the objects. If you move from here to here, then this would be my optical flow vector, right? So what these trajectories do, they follow the object or the point localization. So if you have a fingertip, they follow this fingertip through the object for the video. This trajectory is one of the powerful approaches for videos because it allows you to pre-characterize them, or if you want to find moving objects in videos, you can use the trajectories to be grouped together and factor out the objects in the video. Okay, and then once you have these trajectories, what you do here, similar to what you have seen before, you subdivide the space around the trajectories into histograms of gradients. We extract histograms with gradients and quantize them into different bins. We extract the optical flow. Again, you quantize that as we've seen before. For each of these bins, we extract the histogram of flow. And then you also calculate motion boundaries, which are the difference. It's the difference of the optical flow field. So if you have changes in the optical flow field, you capture that here. So it's the gradient of the optical flow field, and that measures actually if there's a change of, for example, between the object and the foreground and the background. This is actually robust to changes of the camera motion. Okay. Then once you have these features, okay, here's just an illustration. You can see what I said before. It actually nicely follows objects through the scene, and you can see that objects have a similar trajectory, so you can really use that also to group it together and find the objects. You can see also that it's not perfect, right? Optical flow, again, is one of the problems which is not perfect, in particular if you have large displacements, so if you have large motions, optical flow doesn't work, but if you have small motions, optical flow works well. And here these features, you have a set of features for the whole video, which you then summarize together by a robust aggregation scheme, and you can use that. Then, so what you do here, you have these features, you summarize together the bag of features as an aggregation scheme, you add a classifier on top, and then you can actually use that to classify here. This would be the category horses, so we have a set of training images for horse riding competition, and these are, you have here 4,000 hours of videos. These are the 3 best ones which were returned. And so if you just look at them, you can watch them actually. And what's very characteristic for this kind of videos is actually the motion, right? You can see there's this galloping of the horns, and this would be captured by these trajectory features. And so this is the track with multimedia event detection challenge. And what we use here as well is we also use additional channels such as sound and speech. So obviously once you have the descriptors for vision, it's also possible to combine it with other sources of information. So for example, if you have speech, here we work together, this is results which you obtain in my group. If you work together with people who do speech transcription, so you can actually add speech for this kind of event. And you can use sound, so audio descriptions. And we show that this improves the results, obviously, right? Because you have the different channels of optimization. And if you see here, actually this is playing in a music instrument. And here actually the feature which helps you recognize this is obviously not the vision, because the vision is so different that you cannot use the vision by itself, right? And so here what you use is the sound. It does speak, but here it does not. Anyway, so what they do is they describe, actually I'm tuning my harp and blah, 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 so they're saying really what's going on. So this is the feature which is important here, and I think that's one of the things which will come in the future, is how to combine these different types of information together, right? So to move away of separating into individual components, but really to go to something where you integrate, I mean, like the humans do, right? Where we integrate the different channels together and use that together to combine the learning as well as the recognition. Okay, and so the last part here for the current state of the art is actually weakly supervised learning. So this is something which has only appeared in the past few years. So I would say there's no complete state-of-the-art method yet. So really people are just still using relatively simple multiple instance learning methods. And so what's going on here is you have a set of positive images and negative images, possibly with noisy labels. And then what you want to know, for example, you want to localize the objects automatically in the image, right? And so this goes into the direction which I said before. So here you would have the car, and then you use that as a car detector in all image. So here, what we have here, you have annotations, manual annotations of positive and negative images, and then what you want to see is where in the image is the object localized, right? And where this is heading is that you just take a set of noisy annotated images and you learn automatically what's in there, right? And as I said before, basically if you want to learn millions or at least thousands of object categories, you cannot sit there and annotate everything manually, right? You have to think of mechanisms which are either completely unsupervised or at least weakly supervised, that is, maybe you give it initialization and then the system can learn automatically. For example, if a new project comes in, you want the computer to detect that automatically and not sit there and annotate every time something new comes up, label it. I mean, obviously you could do that, but that's not really the goal. So the goal would be really to determine automatically what's relevant here and how to use the noisy annotations which are available to learn actually the content. And here just show one very recent method which we developed in our lab. And so here the idea is actually it's learning from videos. So you have a set of videos which are positive and negative. So you know, for example, here the cow images, they contain cows, but you don't know where they are. And so what you measure if the regions between images are similar. So you extract a set of regions, you have a subsampling of regions, and you measure if these regions are similar between different videos. And within one video, what you do is you track the object throughout the video. So you use the motion information within the video to track it, and then here you measure the similarity. And that's something which people have just recently started working on, like weakly supervised learning from videos. And it seems pretty straightforward because you have the motion information and you have the similarity across videos. But the problem is really how to integrate it and how to put the right confidences to the two, right? And so if you look at the results which we have recently obtained, so here I'm just showing, so we have 10 categories here, just showing one example per category. So here you can see that basically completely automatically localizes the bird just by knowing that there's a bird in there. And the red one is actually completely unsupervised just by knowing that there are recurring objects in the category. It manages to automatically localize the object. You can see here, for example, the cat is moving, so this makes it quite complex to follow the cat in the video. And the hope here is by having these videos that you can really learn the different aspects of the objects automatically, right? By following the cat in the video, you can really see how the cat looks like if it rolls over, or the dog if it springs. Okay, and then two failure cases. So it's always interesting to look when the approach fails and why. And so what goes on here is actually that the background in some cases is more similar between the videos than the foreground, right? So if the bird is sitting, all the birds are sitting on the branches, sometimes the branches are more similar. This shows intrinsic difficulty if you don't know what you're looking for. And then the second example here, the car. Okay, the car is too small. Basically here you can see that the car is going very quickly out of the view and gets very, very small in the end. And again, that's why it fails here. And I guess the problem here with the dog is that it's springing all over the place and there's a lot of camera instability. Okay, and so the last part of my talk will be future research. So what's the future? So today we can deal with concrete problems and subcategories well, like faces, pedestrians, image retrieval. And what you want to do in the long run, you want to really learn how to model visual knowledge from large-scale data, or at least that's what I want to do. And so basically what we have today, we have this very large collection of images and videos which come with metadata. So you have many of them with annotations, which you can then use as weak labels. And so the two open questions are, how do we do large-scale learning? How do we use this large collection of images? And how do you use all this data which is there to weakly supervise learned information? How do we build a knowledge base, right? Because what you do today, when we train our algorithm, every time we retrain it from start, right? So we sit there, student comes, sets up the program, takes the images, runs the classifier, goes home, throws it away. So there's there's a bit, but there's almost no incremental learning, right? There's maybe incremental learning in the sense that there are a few categories which it works, but there's no incremental learning and no reflection on how to use the knowledge which has been there before. So basically, the idea would be we have this large collection which is online available. We might annotate some of the data ourselves because maybe it's too difficult to do it completely unsupervised, but then we really want to update the models over time and be able to handle this. Okay, and so in my opinion, what are the three different problems here? So the first one is we want to go away from like individual objects. So far we have seen either we want to categorize images or classify individual objects, but what we really want is to interpret the whole scene, so really know what's the content of the scene. Then we want to determine how to really learn jointly from vision, text, and sound. And then there's a whole set of machine learning problems, which is large-scale learning and optimization. And they obviously, all the three of them are interleaved, right? Because they all play together. Okay, and so what we want, if you want to understand an image or a video, what we really want is to know who is sitting on the motorbike, where are the dogs, what kind of dogs are there, and so forth. So if you want to have answer any generic question about the image, that's the kind of representation which we really would like to have. Of course, maybe just a sub-part of that, right? And the advantage, if we go towards these representations, it makes the task also easier because they can play together. And if you know that here either you have a motorbike or maybe a bike or maybe something else, and here's a person, then you can determine by the relation between the objects what's going on there. Okay, and so how do you want to do this? We want to do this by actually modeling, getting much more structured representation of the scene, right? So for now we have these individual components. Here the idea would be to go, for example, link together different deep learning structures into higher level representation where we have another layer where we connect all the different components together. And then for online learning from vision, sound, and text, so for now what people do, they use multiple instance learning and discriminative clustering. People also learn from video streams with weak labels. And what you have to really do is to align the image and video with sound and text. So one thing is to really see how to do a precise alignment. If you know that, for example, open door, stand up and shake a hand follow each other in a sequence, you want to determine precisely where it's in the image. You want to, if you have an image in the video, if you have an image, you want to precisely determine where in the image these different components are. So that would be the alignment technique. And then something which is also very important is how to update the memory structures online over time. So if you have a knowledge base, so how do you set up such a knowledge base, and how do you update it over time incrementally? So we've seen these deep neural networks. You can update them a bit, but today it's not clear actually if you relearn what components are updated, right? Because in general it's just the higher levels which change. And so there it's really important to see what's going on, what you learned, and how you store the information and update it over time. And then large-scale learning optimization. Still, if you want to update or optimize these huge models and have this large amount of data, you still have to speed up your computation because even if you have larger computers, you cannot do it in a reasonable time. And it's important to develop on the learning side weakly supervised and unsupervised learning methods. And then something which is also very important is how to optimize these deep learning architectures automatically. So what people do today, they just set them up manually. They go and train and test, then change a bit the model, but they claim it's all learned, but in the end, there are many different components which are handcrafted still. So here the idea would be to go further and really see what kind of structures can you learn automatically and how do you adapt to the data automatically. Not just every time you have a different problem, you adapt those networks to the do the problem manually, because then you still have this problem of manually doing it, okay? And then we're also looking at an alternative approach to deep networks, which are deep kernel machines, where there actually the idea is that you understand better what's going on by modeling each layer individually by a kernel where you look first at how the network actually works. Okay, so thank you for your attention. If you have any questions.